This video is about precipitation reactions, which is our next topic in Chapter 4. And so precipitation reactions, back in Chapter 3, we talked about various ways of classifying chemical reactions, and one of them was double displacement reactions. Precipitation reactions are a subset of double displacement reactions. And if you'll recall, a double displacement is a partner swapping reaction. And so you can see here that we start out with A matched with B and C matched with D, and after the reaction we've got A matched with D and C matched with B. In the case of precipitation reactions, components A, B, C, and D are all going to be ions in ionic, and so the compounds AB, CD, AD, and CB are all going to be ionic compounds. Before we talk about this, I want to go ahead and hammer back on something we've talked about before, which is trying to, and really at the core of Chapter 4 is this idea in the very first section of trying to understand what's actually happening when you dissolve an electrolyte in water. And so when an ionic compound dissolves in water, and as you'll recall, soluble ionic compounds are electrolytes, and remember an electrolyte is something that gives you ions in aqueous solution. But when an ionic compound dissolves in water, it's going to dissociate into its constituent ions. And so if I say that I've got aqueous silver nitrate, what I'm really saying, and that's what the equal sign means, if I say I've got aqueous silver nitrate, what I really mean is I've got a mole of aqueous silver ions and a mole of aqueous nitrate ions, because once the compound dissolves in water, those ions diffuse away from each other and they're no longer associated with each other. So having a mole of aqueous silver nitrate is really saying I've got a mole of aqueous silver ions and a mole of aqueous nitrate ions. That's an example in which the ions are there in a 1-to-1 ratio. Think of a compound like calcium chloride, in which there is one calcium ion and two chloride ions in the formula unit. So if I have a mole of calcium chloride that is dissolved in water, what I'm really saying that I have is a mole of calcium ions plus 2 moles of chloride ions, and they have all separated from each other and diffused away from each other. In a more streamlined way, we would characterize this as saying that if I've got a mole of calcium chloride, then I've got a mole of calcium ions plus 2 moles of chloride ions. So this is a more formal way of describing what I've got here. Okay, now that's what happens if I just dissolve one electrolyte in aqueous solution. What happens if I mix 2 different electrolytes in aqueous solution? What will I end up having? Well, I can start with a very simple example, which is to take a solution of potassium chloride and mix it with a solution of sodium bromide. And so what do I get? When I dissolve potassium chloride in water, so if I dissolve a mole of potassium chloride in water, I get a mole of potassium ions and I get a mole of chloride ions, and they are separate from each other in solution. If I then add to that a mole of sodium bromide and it dissolves, I get a mole of bromide ions and a mole of sodium ions. Now you'll notice that what I actually have is just a collection of ions that are just kind of sitting around staring at each other. They arrived in the solution this way, that potassium was with chloride and sodium was with bromide. But I could just as easily now, because they're all just collected in aqueous solution together, I could say that I've got potassium bromide and sodium chloride. So what compounds do I actually have? Well, I actually don't really have any compounds. I just have a collection of ions sitting in solution staring at each other. But the point I'm trying to make here is that if I dissolve potassium chloride and sodium bromide together in water, the result is going to be the same as if I had dissolved potassium bromide and sodium chloride together in water. I'm just going to get a collection of the same 4 ions that are just floating around in aqueous solution, staring at each other and not doing anything. Now that's the case when I mix these 2 particular compounds, but I can mix things to give me a combination that is not water soluble, because not every ionic compound is soluble in water. And so it is possible to mix a compound that is water soluble with another compound that is water soluble, and then get a combination that is not water soluble. And when those ions see each other, they're going to form a solid and separate from solution. So one example of this would be to mix potassium chloride with silver nitrate. Potassium chloride is water soluble. So when I have a solution of potassium chloride, that means I've got a solution of potassium ions and chloride ions that are separate from each other. Silver nitrate is soluble in water. So when I have that in solution, I've got a collection of silver ions and a collection of nitrate ions that are distinct from each other. When I mix the two solutions together, I actually get a combination that basically can't stand to be apart from each other, and that is silver and chloride. And so silver and chloride will actually form a crystalline solid, which forms what's called a precipitate. And a precipitate simply means, precipitation simply means to fall. So it comes from the idea of a precipice or a cliff, falling off a cliff. We think about rain or snow as being precipitation. That's because it's falling from clouds in the sky. And if a solid suddenly just emerges and falls from a solution, we call that a solid precipitate. And so when we mix potassium chloride and silver nitrate, this solid precipitate of silver chloride will separate from the solution and just crash to the bottom. And so we can actually take a look at an example of this.
When moderately concentrated solutions containing silver ions and chloride ions are mixed, the resulting solution is supersaturated with silver chloride. A precipitation reaction occurs until the system reaches equilibrium. In this model, the red and white molecules are water. Chloride and silver ions, gray and green respectively, are in solution. When they encounter each other, they bond and bind with other silver chloride molecules that have precipitated from solution to form the solid.
Okay, now I don't really like the way that she was using the word molecules there to describe an ionic compound. But what it does show is that when you mix potassium chloride and silver nitrate, you get that precipitate. And there are many other examples of precipitation reactions. This is actually, the one that's shown on this slide is actually something I did for the parents at Parents' Night earlier this year, in which you mix lead nitrate with potassium iodide. And it's pretty cool because you have two completely clear, colorless solutions. And when you mix them together, you get this cloudy yellow precipitate. So a precipitation reaction, just to formally define it, is what occurs when you mix ions that are soluble, that were solubilized when you mix them, but when they get together, they form a combination that is not soluble in water. And so a precipitation reaction will occur, a precipitate will form. These are also, so double displacement reactions are also known as metathesis reactions, and metathesis just simply means to exchange or transpose. And so if I take silver nitrate and potassium chloride and I transpose the cations and the anions, I'm going to get silver chloride and potassium nitrate. Potassium nitrate is soluble in water, but silver chloride is not. And so it will precipitate out of solution, just as we saw in the video there. Now, the question that's going to arise for you is, how will I know if a precipitation reaction is going to occur? Because what I've just done is given you two examples. And one was, if I mix sodium chloride with potassium bromide, nothing happens, because sodium chloride, potassium bromide, sodium bromide, and potassium chloride are all soluble in water, and so nothing happens. Whereas if I mix potassium chloride and silver nitrate together, although potassium chloride is water soluble and silver nitrate is water soluble and potassium nitrate is water soluble, silver chloride is not, and so I get a precipitation reaction. So I've given you an example where it will occur, and I've given you an example where it won't occur. How are you going to know? Well, the way that a typical, say, college level general chemistry student would know the answer to that would be to memorize a fairly exhaustive set of solubility rules. And you have this list of solubility rules in your textbook. The thing is that when it comes to AP chemistry, the College Board actually does not require you to memorize all of these detailed solubility rules. In fact, they just want you to memorize a very, very simple set of solubility rules. But the bad news about that is while you don't need to memorize a bunch of solubility rules, it doesn't answer the question of when is a precipitation reaction going to occur and when is a precipitation reaction not going to occur. Well, here is the list of solubility rules, not that's in your textbook. This is actually from a McGraw-Hill textbook, but what's in your textbook is very, very similar to this. Once more, you don't actually need to memorize all these rules. This is all you need to memorize. These are the College Board solubility rules. All salts, or that is all ionic compounds that contain sodium cations, potassium cations, ammonium cations, and nitrate anions are going to be soluble in water. So anytime you've got a compound that contains one or more of those ions, it will be water soluble. Okay, so what does that tell us here? It tells us that if I mix potassium chloride and sodium bromide in water, that I will not get a precipitation reaction because potassium chloride contains potassium and all potassium salts are soluble in water. Sodium bromide contains sodium and all sodium salts are soluble in water. We look at it this way, potassium bromide contains potassium. All potassium salts are soluble in water. And sodium chloride contains sodium, and all sodium salts are soluble in water. And so what the, well, let me back up. I mean, let's keep going, and then we'll sort of get to the conclusion here. By contrast, if I mix potassium chloride and silver nitrate, potassium chloride contains potassium, it's water soluble. Silver nitrate contains nitrate, it's water soluble. Potassium nitrate contains both potassium nitrate. It is therefore must be water soluble. Silver chloride doesn't contain either of those, but that doesn't actually tell you whether there's going to be a precipitation reaction or not. You actually have to mix them and find out. So really, it turns out that there is, but what the College Board solubility rules don't do is to allow you to predict a precipitation. They will allow you to rule out a precipitation. So in the case of combining potassium chloride with sodium bromide, what the best the College Board's rules can do is to allow you to rule out a precipitation. They do not allow you to predict a precipitation. So you're back to where we were before, which is how are you going to know there's going to be a precipitation? Well, here's how a problem would be presented to you that would allow you to answer that question. Aqueous solutions of potassium chloride and silver nitrate were combined and a precipitate was seen. Okay, aqueous solutions of potassium chloride and silver nitrate were combined and a precipitate was seen. We know there's a precipitate because the problem tells me there is. Now all I have to do is predict what it's going to be. Well, it can't be potassium chloride because potassium chloride has potassium. Potassium salts are always soluble. It can't be silver nitrate because silver nitrate has nitrate and all nitrate salts are water soluble. It can't be potassium nitrate because potassium nitrate has both potassium and nitrate and all potassium salts and all nitrate salts are soluble in water. And therefore it must be silver chloride because that's the only combination. If the problem tells you their precipitate was seen, this is the only combination that does not contain ions that are always water soluble. So that's going to be your precipitate. Okay, let's talk about some things that we can do when it comes to looking at a precipitation reaction and finding out what's actually happening. It's helpful when you're doing this to pay attention to just what species are present there in the reaction mixture. That is, whether they're solids, whether they're liquids, whether they're aqueous solutions. etc. If we're going to understand what's actually happening in a particular precipitation reaction, we have to be aware of what is changing during the course of the reaction and what is not changing. And that leads us to what is a set of equations known as molecular equations, ionic equations, and net ionic equations. So let's go back to our potassium chloride plus silver nitrate reaction. This is what's called the molecular equation. Now, we've talked about the fact that ionic compounds are not molecular compounds, and these are not molecules, but they're written as if they were. In other words, silver nitrate is written as if it was a single thing, not just a collection of ions. And potassium chloride is written as if it was a single thing, silver chloride, potassium nitrate. So we call this the molecular equation, but I would put that term molecular equation in quotation marks. We're writing them as if they were associated with each other, but they actually are not. So here's the reaction that occurs. Silver nitrate, when combined with potassium chloride, causes a precipitate of silver chloride to be produced, plus what remains is an aqueous solution of potassium nitrate. Now we can take that and turn it into what's called an ionic equation. And an ionic equation is going to recognize what we were talking about at the beginning of this video, which is that when I take a soluble ionic compound and dissolve it in water, what species are actually there. And so we're going to take all ionic compounds, and later in this chapter you're going to see it also. We'll do this with strong acids and strong bases. And we're going to dissociate them into their ions. And so that's going to more accurately reflect all of the species that are actually in the reaction mixture. So here is my molecular equation from the previous slide. Now I'm going to take everything that is listed as being aqueous and dissociate it into its constituent ions. And so aqueous silver nitrate becomes aqueous silver plus aqueous nitrate, because that's what you actually have when you've got aqueous silver nitrate. Aqueous potassium chloride becomes aqueous potassium ions plus aqueous chloride ions. Solid silver chloride, because it is a solid and won't dissolve in water, does not dissociate into ions, and so that remains the same. It remains as solid silver chloride. Aqueous potassium nitrate, in the ionic equation, we dissociate it into aqueous potassium ions plus aqueous nitrate ion, because that's what's actually there in solution. Now, the next thing to do is to take that equation that I just had, the ionic equation, and look for things that appear to be exactly the same on both sides of the equation. And so if you look carefully at this, you'll see that there is an aqueous nitrate ion on the left-hand side of the arrow, and an aqueous nitrate ion on the right-hand side of the arrow. There's an aqueous potassium ion on the left-hand side of the arrow and an aqueous potassium ion on the right-hand side of the arrow. And so we can simply cross out both the nitrates and the potassiums because they are not changed from one side of the arrow to the other. They just remain as aqueous ions in solution. By contrast, while there are silver ions and chloride ions on the left-hand side of the arrow, there are not solubilized silver ions or chloride ions on the right-hand side of the arrow. It's actually solid silver chloride. So because this is different from either that or that, we don't cross them out. These ions that we've just crossed out are called spectator ions. They're called spectator ions because they're not actually doing anything. They are appearing the same on both sides of the equation. And so their purpose is simply just to sort of chaperone the reacting species into solution. In this particular case, the spectator ions are potassium and nitrate. Then finally, to get what's called the net ionic equation, we simply write what's left after we have removed the spectator ions, and what's left is silver ions plus chloride ions give solid silver chloride. So we cross out anything that doesn't change from the left side to the right. Those are the spectator ions. We remove them, and the only thing that's left in the equation that is actually changing is silver ions plus chloride ions going to solid silver chloride. So here's a summary of how to do that. Writing a net ionic equation. You're going to write a balanced molecular equation. Once again, the term molecular really should be in quotes because it is an ionic reaction, but the molecular equation shows the ions as if they were associated in compounds. Then we dissociate our ions and form the ionic equation. Then we identify and cross out the spectator ions. Those are the things that remain unchanged from one side of the equation to the other. And then we rewrite the equation without the spectator ion, and that gives us the net ionic equation. Well, there will be some practice problems posted with the assignment for this, and there will be a QOD in the morning. Thanks for watching.